Will do. And to be honest, I'll maybe plan to speak for a little less than 17 minutes since I know this has been a long day. And at least for me, it was overwhelmed with lots of information. So I'll try to keep this short and fun and maybe end on a somewhat lighter note. So what I'm going to tell you, not that, I mean, today was incredible. So super, super great day. So what I'm going to tell you about today is some work I've been doing on turbulent radiative mixing layers. And you can see one of these simulations in the background here. And in general, I should say I'm an astrophysicist. And so as such, I'm going to butcher a lot of your favorite terms here. Like I'm going to use the term turbulence somewhat imprecisely. But I'll try to be clear throughout. So in general, what I'm going to tell you about is part of a larger effort to build a sort of physics first formulation of galaxy formation, right? Galaxy formation is one of the major unsolved problems in astrophysics. And we're at this place right now where we are getting really exquisite observations of galaxies that provide a really amazing window into the incredibly complex, diverse, turbulent, and multi-phase nature of galaxies. And now I guess another place where I'll be imprecise, since we've had talks on multi-phase turbulence today, what I should be clear when I say multi-phase, I don't mean liquid droplets suspended in air. Instead here, I mean fully ionized plasma, where you have very hot plasma and very dense plasma co-spatial and interacting with each other. And actually you can see that here, these sort of transparent areas are where there is a hot dilute plasma, and the brown regions are where there is a denser plasma, but it's not truly multi-phase in the technical sense of the word. But okay, so that nonetheless, right, we're getting these amazing observations, and we're now working very hard to build up a theoretical understanding of how the phase structure of galaxy develops and how it's related to the overall evolution of galaxies. And our simulations, like you can see here, are doing a pretty good job, I would say. So here's a simulation. I chose this to sort of look quite similar, if I flash back and forth, look quite similar to the observations. And what I'm showing here is a galaxy viewed face on, where I'm visualizing the temperature. Now, the bright blue gas is around 100 Kelvin, and the bright yellow gas is around 1,000,000 Kelvin. I'm going to use this same color map throughout. So you can really just think of bright blue as cold and bright yellow as hot. And, as you can see, we get a really rich and interesting set of dynamics within the interstellar medium. But if I slowly zoom out and sort of flip this galaxy around, you can see there's all kinds of very rich dynamics going on, not just within the galaxy, but also around it. You can see there are 3 satellite galaxies. There's a long sort of cosmic weather feature, you might think of this as. This is sort of cool and cold gas raining down onto the galaxy, some of it being stripped out of the satellites. And there's all kinds of really important interactions going on in and around galaxies. And it's really these galactic gas flows that hold the key to developing a real predictive and robust model for galaxy evolution as a whole. It's because, and you can't really just focus on the galaxy itself. You need to look at the overall environment. Okay, so these galactic gas flows are super important, but there's a lot of difficulty when it comes to modeling them. So let me just highlight one of the main difficulties, which is the separation of spatial scales. And all of us study turbulence in some degree or another. we saw some Rayleigh-Bernard convection with Rayleigh numbers of 10 to the 25 or so. Here we're going to see similarly highly turbulent systems where we have, Reynolds numbers on the order of 10 to the 18 or so. Now, that's what it would be if we were able to resolve everything down to the smallest scales. Unfortunately, we're not. So we make some cheats, which I'll describe. But the problem stems from, as I said, this multi-scale nature. And so in the background here, I'm showing a slice of the cosmic web. If you haven't seen one of these images before, I guess let me show this. This is the dark matter density in a patch of the universe at the present day. And you can see there's these long filaments that are connecting these bright nodes, and these nodes are called dark matter halos. And in the centers of these halos is where galaxies reside. But when we look in the gas filling the halo, which is what I'm showing here, which happens on scales of a megaparsec, which is about 3 million light years, there's highly multi-phase gas, this same hot, cold color map here. And you can see there's all kinds of rich dynamics on large scales, which comes from the driving and accretion onto the system from large scales, which is driving turbulence, heating the gas, doing lots of things. But if we zoom in by a factor of 1,000 into the center here where there's a galaxy, here I'm showing a little slice through the midplane of a galaxy, there's a whole nother set of really important, rich phenomena that are, as you can see here, this is where a bunch of supernovae have just exploded. They've ripped out of the galaxy and they're driving energy back out into the surrounding medium. And so there's not only these large scale flows, but there's also these intermediate scale flows. And as you can probably guess from the slide layout here, that's not the end of the story. If we zoom in again, another factor of 1,000 or so onto the skin of one of these hot cold interface regions, you can see here I've got it oriented horizontally with the hot on top and cold on bottom, with this highly dynamic turbulent mixing layer separating the two phases. And so this is meant to highlight the really daunting range of spatial scales here, where we have dynamics at play that are essential for modeling galaxies spanning at least 6 orders of magnitude. And that's only to, barely resolve the mixing layers, right? You'd really have to go to many more orders of magnitude. And it's volume filling. So it's really quite a challenging problem. Adding to that is these dynamics are fully interconnected. So it's not like we can really separate them and study them one at a time, because the large scale flows impact the small, intermediate, and smaller scales. Likewise, the small scales determine the overall energetics and phase structure of the intermediate and larger scales. So it's a quite challenging problem, I would say. Great. So let's take a look at one of these multi-phase galactic winds. So that's this little simulation I'm showing here. And to situate people, this is showing a 2D slice of the temperature field through a 3D simulation, which is meant to represent a little patch of a galaxy. Okay, and this is work done by a great former Santa Barbara graduate student, now postdoc at the Center for Computational Astrophysics with me, Brent Tan. And what we did was we studied this process of supernovae driving outflows out of galaxies. And I'm going to take that simulation, flip it on its side. So now the galaxy is oriented vertically, and I'm going to make this a movie. And what you should imagine here is, here's the midplane of the galaxy, right? These bright blue things are cold, dense clouds. And there's going to be hundreds of stars that have just formed right here in the center. And they're going to explode as supernovae, which rip through the interstellar medium, drive this turbulent bulk outflow up out of the galaxy, driving this highly multi-phase galactic wind. Okay, so right there is I would say a really solid background on why we're so interested in, multi-phase fluid dynamics and, turbulence in general, and in particular multi-phase turbulence and mixing layers in particular in the, modern astrophysics on a galactic scale. And there's some really key questions that we're starting to address when looking at these systems. In particular, one that's very near and dear to my heart is what actually accelerates the coldest phase. So here I've circled an individual cloud. This cloud here is just starting to get picked up out of the galaxy and launched into the surrounding medium. And in reality, so in the real universe, when we observe galactic winds, which we do very commonly, we often see cold gas flying at hundreds or thousands of kilometers per second up out of the galaxy. Now, in these simulations, the hot gas is going hundreds or thousands of kilometers per second, but the cold gas is only going, a few tens to maybe 100. So there's a real conundrum which stimulated the field for a very long time. A lot of the best work coming out of Santa Barbara over the past, say, 5 to 8 years, led in large part by Peng O, who's going to be talking later this week. And what we as a community have realized is that this acceleration process can be understood by sort of taking your cloud and zooming in onto the skin of the mixing layer, of the cold cloud, which I like to call the turbulent radiative mixing layer. And we add radiative because these plasmas have a really important property that they are optically thin to their own cooling radiation. So as you collisionally excite these partially ionized elements, the electrons get excited and then they can radiatively de-excite, allowing that energy to leave the system. And that's a really crucial aspect in these turbulent mixing layers, which are so important in regulating the overall energetics and phase structure of galaxies. So I'm going to tell you now about some work that I did a few years ago and that I recently did a follow-up paper with Zurui Chen, who's now a graduate student at Santa Barbara. So as you can see, there's a big Santa Barbara connection here. Uh-oh. And my headphones may have just died. Can the audience still hear me?
Yes, we can hear you.
Okay, cool. It seems like only one of my headphones have died, so I'm gonna keep on going, and hopefully the other one survives for long enough, because we're almost there. So the basic idea here is that we have cold gas on the bottom, hot gas on the top, and they're moving relative to each other. And this shear flow gives way to the Kelvin-Helmholtz instability, which in turn leads to the development of turbulence. This turbulence mixes the two phases, which enables the hot gas to radiate away its energy via this collisional excitation and then radiative de-excitation process. And this loss of energy leads to a net condensation from above of the hot phase down into the cold phase. And what's really crucial here is this brings in, fresh material into the cold phase, but it also crucially brings with it its kinetic energy, okay, and its momentum. And so it's this act of cooling induced condensation which actually is responsible for accelerating these cold clouds up to very high velocities. And so the basic picture we've developed over the past few years is that the shear flow gives way to turbulence, turbulence mixing, mixing cooling, cooling condensation. Good, got it. So that's the basic picture. To be perfectly honest, I thought I would have gotten through this in about the first 5 minutes or so, but I guess I'm a little wordier than I expected. So I'm just going to sketch out very briefly in the last minute or two the actual predictive model that we developed for this. And here's the basic picture, okay? So here's our mixing layer. The cold is on the bottom, hot's on top. We've got our pink interface. This is where all of the cooling happens. And it leads to an inflow. okay? And so the basic model is that the flux of enthalpy from above, given here, where we've assumed an adiabatic index of 5/3, is balanced by the total cooling, right? Pretty simple, it's just steady state. However, right, oh yeah, sorry. So if we solve those two, we equate them, then we get that the volume divided by the area squared divided by the cooling time, the rate of cooling, gives you this inflow velocity, which is really the key thing that we're after. But we don't know what the cooling volume actually is, right? It's some area of this bumpy, wiggly surface times some thickness. So I'll just sketch out briefly how we estimate these two things. First, the width of this, cooling thickness, this cooling layer. It's a very, very simple argument. So if we actually measure, say, the power spectrum or the structure function of the turbulent velocities within this mixing layer, it's remarkably Kolmogorov-like. And so you get a structure function where the turbulent velocity scales with the length scale to the 1/3 power. And so if we consider the scale-dependent mixing time, which is just the length scale divided by the turbulent velocity on that length scale, then we get that goes as L to the 2/3 power, right? So more rapid mixing on small scales, we all know that. The cooling time is just a number, okay? But you can see that this picks out a crucial length scale, which we call W, which is the length scale above which cooling beats mixing and below which mixing beats cooling, right? And so this is the region, this is the sort of thickness of the cooling layer. Now, I'm already at 17 minutes, so I'm just gonna say that the area here is bumpy and wiggly, but right, we can be more precise than just bumpy and wiggly. We can say that it's a fractal, right? And so you can think of this as a sinusoid with smaller sinusoids layered on top of it, which is sort of what you would expect from Kelvin-Helmholtz, since the small wavelength modes always grow faster than the large wavelength modes. And and so this is sort of what you can imagine as you get to, a large amplitude. You'll always have smaller amplitudes that are already saturated. Now, great, so I'm just going to say that with analogy, we can make analogy to the Koch curve, which has a fractal excess dimension of 1/2, just like a crumpled piece of paper, one of my favorite examples, or a Brownian surface. And so we can go into the actual simulations, measure the fractal dimension. I'm going a little fast here because I'm out of time and it's maybe not the most interesting, but we can measure the fractal dimension, find that is indeed has a fractal excess of 1/2 or a fractal dimension of 2.5, which allows us to predict the area on the scale W as well as the width W itself. And we can put this all together and we get this really sort of nice, although somewhat counterintuitive expression for the inflow velocity. It's just the turbulent velocity times this ratio of the mixing time to the cooling time to the 1/4 power. And so it's really this fractal surface, which I'm visualizing here, that controls the net transfer of mass, momentum, and energy between the phases, where we have, right, the cooling is just the enthalpy times this inflow, the mass flux is the density times this inflow, and the momentum flux is the momentum times this inflow. So there's a whole second part of the talk, which I'm not gonna even bother to show, but I'll end there and maybe take a few questions.
Okay. Thank you very much.
Yeah.
Questions?
Hi, Drummond. How do magnetic fields affect the interfaces?
Oh, fantastic question. One I was hoping not to get. Whoops, where am I going here? So this has actually been a very hot topic in recent years, or really in recent months. So yeah, so the magnetic fields can dramatically impact the mixing layers. But there's somewhat of an issue here, which is as you saw in these simulations, we're using a doubly periodic box with outflow conditions on the top and bottom, which is a really good way to have your magnetic fields get wound up very, very tightly. And so what you can imagine is you include magnetic fields, even very weak magnetic fields, a plasma beta of 1 million or so. Within not too long, you will have tangled that magnetic field through the small scale dynamo process and built it up to a point where it's dynamically important, and then it can completely shut off mixing. Okay, so that's an indication that this is completely worthless, everything that I've shown you. However, what has recently been shown, and again, I'll maybe punt to Peng's talk later this week, what has recently been shown is that when you actually include the more global geometry, so not just the skin of the cloud, but the whole cloud itself, then the magnetic fields are able to, they still change the flow dramatically, but they don't get amplified to the same extent. And so it's a really unanswered question, I would say. But it seems like there's some mesoscale phenomenon which takes place that's sort of missed in these smallest scale boxes.
Thank you. That's very interesting.
Okay, other questions?
It seems there could be an analogy with deflagrations, such as in astrophysics, the deflagration leading to supernova detonation, in the sense that instead of having the cooling generating a condensation flow, you could radiatively, convectively, and so on, heating up the surroundings. The synergism between the phenomenology and modeling that you described or in other such cases?
Yes, absolutely. It's a really, really great question. So it turns out that there is another competing model for the way this all works that doesn't invoke fractals and is led by the Santa Barbara group, led by Peng O. And their model is entirely based on the theory of turbulent combustion, which is, as you said, very similar to the deflagration process. And so I think there is a huge amount of similarity. It's just a real minus sign. Although, maybe Peng can say something on this, but I don't know, we've learned a lot from the deflagration and combustion communities. I don't know if any of our insights have trickled back up. It would be interesting to think a little more about that, because we've certainly found some quite interesting details. There's a whole second half of this talk which I didn't get to, which I think would be new to that community as well. So it'd be fun to think a little bit about that.
I have actually a comment and maybe a little question afterwards. In general, my impression from your talk, very nice figures and great analogies, that quite often turbulence, especially in these interdisciplinary aspects, it's used like as a synonym for complexity. However, when we interpret data, especially when it's an astrophysical data, it's also good to keep in mind that turbulence is a very specific process. For instance, it's a stochastic process that doesn't have memory of initial conditions, or it's a super diffusive process with larger velocities as larger length scales. And quite often in realistic scenarios, these aspects are not being checked. This is actually quite often turbulence is indeed used as a synonym for a complexity. And reality may have many more secrets. And in this sense, actually, and provide food thought and also open new venues for exploratory research in astrophysics as well as in fluid dynamics or plasma physics. And what is also important that astrophysics actually in this case has this very special niche, in a sense, very special word to say, because a quantification of power laws, accurate quantification of power laws, which is very important for any similar process, including multifractal processes or turbulence or similar mixing. It actually first was done in astrophysics backed by Kepler, because in Kepler's third law, one has a different velocity scalings and which exactly identifies the physical structure. And it might be good just to keep it in mind. So My question to you would be maybe a little bit on a more technical side. So that was my,
Sure.
my question. When you talk about evolution of galaxies, based on the data that you actually trying to analyze, how well the galaxy motion is resolved? For instance, like, how many data points do you usually require to consider the galaxy as being a well-resolved galaxy in a sense?
Yeah. Great. So I could answer that for a really long time. First, allow me to just address your comment. So what's nice about these mixing layers is the velocity field does forget its initial conditions. The velocity field does exhibit classic, turbulent power spectra and structure functions where the velocity fluctuations are larger on larger spatial scales. So it's not like purely just being used as a byword for complexity. We do think a little bit about the actual turbulent properties and to what extent we can and cannot extrapolate from isotropic homogeneous turbulence to these highly disordered, very, very different systems. So that's something, I do agree that there's a lot more that can be done there.
Yeah,
And then to your,
the dynamic range actually, right?
Sorry, say that again?
The span of scales, dynamic range, the ratio between the largest and the smallest resolved scale, it should span several decades in a well-resolved turbulent process.
Yeah, so these simulations are 4,000 cubed. So we have a pretty nice separation of scales. Our inertial range is about 2.5 decks before we hit the viscous and conductive scale, which starts to, deviate the power spectrum. So I think, these simulations in particular are fairly nicely resolved, I would say. When we're talking about simulating entire galaxies, right there, it becomes a matter of what are you trying to resolve? Because, when you're resolving a whole galaxy, this mixing layer that I'm showing here takes place on, 1/billionth the scale of an entire galaxy. And so we're not resolving the galaxy with 1 billion particles or 1 billion separation of scale. So, generally people try to do their best and say, if we're going to try to get the phase structure, then we need to resolve supernova remnants, or if we're going to try to resolve, say, the bulk flow, then we need, X number of cells. But it's a real moving target, and I would say a point of real imprecision in the astrophysical community that's constantly leading to disagreement. So maybe I'll leave it there.
Okay, I think that's a good time for us to wrap up. Now, thank you very much for a very interesting talk.
Yep, thanks everyone.